Hi everyone, welcome to the second lecture of this fifth week module where we are discussing humidity and chemical sensors. In the previous class, we have discussed about humidity, particularly its definition, its mathematical representation, and we also discussed some uh, actual humidity sensor, particularly based on optical phenomena. Today, we will try to discuss some more type of humidity sensors. Okay, we are going to start with the gravimetric humidity sensor first. Okay, so a gravimetric humidity sensor or a hygrometer measures humidity by separating the water from gas. Okay, so it subsequently determines the masses of water and the gas separately. So consider this diagram where you have balance, okay, and there is one heater which heats this water through this porous plate, okay, and this water absorbing material absorbs the humidity, and the balance actually measures the weight of the moisture. Okay, so this balance can be a micro balance also. So depending on what kind of gravimetric sensor you have, you may have different kind of balances. Okay, so these masses, the mass that this balance measures actually is used to calculate the mole fraction in the gas. Okay, so other humidity quantities, for example, we discussed yesterday different humidity quantities, particularly the absolute humidity, the relative humidity and specific humidity, and we discussed that relative humidity is of utmost importance for us, particularly because of its importance in the industrial applications. Okay, so when you have this mole fraction of humidity through this micro balance, what you can do is you can use it to calculate the relative humidity. Okay, however, this determination needs some more factors to quantify. Okay, like the additional measurements can be, say, measurement of saturation vapor pressure or say partial vapor pressure, even though you have the mole fraction of water molecules. Okay, and of course you should know the temperature of the gas made, which has entered before and after the measurement. Okay, so the first type of gravimetric humidity sensor is a SAW type device. This SAW is abbreviation for a surface acoustic wave device. Okay, so surface acoustic waves are nothing but sound waves that travels along the surface of a elastic material. Okay, so if you have an elastic material, the sound waves can propagate through it. Okay, of course, it, as the name suggests, it's a surface wave. So basically it can penetrate maximum to say one wavelength of the wave that is propagating. Okay, so the amplitude of the SAW wave decreases exponentially as they move into the material, confining them to a depth of about wavelength. Okay, these waves are also known as relay waves. Okay, so this is a schematic diagram for a SAW sensor. You can see that you have a quartz substrate, okay, on which you have this vapor sensing film through which this sound wave will propagate. Okay, so this is output IDT and this is input IDT. Okay, one acts as a source of sound wave and one acts as a receiver of the sound wave. Okay, and this vapor sensing film provide the delay path. Okay, so the relative humidity can be determined by measuring the relative change of the phase velocity of the sound wave. Okay, the relative change in the phase velocity and frequency are related by the expression del V by V naught equal to del F by F naught, where F naught is the SAW frequency, while this delta F is the frequency shift caused by the vapor absorption. Similarly, this V naught is the phase velocity of the SAW wave, and del V is the change in the phase velocity. Okay, so this del V by V naught can also be written as minus pi h V naught square by 2 lambda into del rho into ax square plus ay square plus az square, where this ax, ay and az are normalized displacement amplitude of the SAW wave, while this lambda is the acoustic wavelength. Okay, this del rho is the change in the mass density, okay. H is the film thickness, okay. V naught is the saw phase velocity that we have just seen in the previous slide, and del V is the relative change in the saw phase velocity, okay. So this is the expression of del V by V naught, and from the previous equation we have seen that this is equal to del F by F naught, okay. So to understand this, we have to first understand the phase velocity. So there is a concept of phase velocity and group velocity, many of you might be knowing also. However, I will just describe in brief what is the phase velocity that I am talking about right now, okay. So the phase velocity is the speed at which a wave's phase propagate through space, okay. So it is the speed at which the phase of any one of the wave's frequency component travel, okay. So phase velocity is highly dependent on the wavelength and time period, while group velocity is the speed at which a packet of wave moves, okay. So now I am not talking about a wave, but I am talking about the packet in which the waves are moving, okay. So it is the velocity with which this wave packet travels, and it is the speed at which the peak of actually wave packet travels, okay. So group velocity is nothing but the phase velocity plus k into del Vp by del k, where this Vp is the phase velocity and k is the angular wave number, which is equal to 2 pi by lambda, okay. So this concept we know from the propagation of wave concepts, okay. So the velocity that I was talking in this saw device was actually this Vp, okay. So this is the first type of gravimetric sensor. Then there is another concept of gravimetric sensor in the form of quartz crystal microbalance, or sometimes known as QCM based sensors. So QCM based humidity sensors are also very popular and very precise, okay. This is shown by the mechanism of quartz crystal microbalance based humidity sensor is shown as a schematic diagram in this figure. You can see that the operation of this sensor is based on shift of the resonant frequency f, which shifts away from its resonant driving frequency, another component fr, when an additional mass m is deposited on the sensing film, okay. So this is your sensing film, and what I am trying to do is I am trying to measure the this quartz natural frequency, okay. So this natural frequency will of course shift when I have loaded this film with some material, okay. So this molecule that I am loading on it, if it is a, say if this film, this QCM film, if I made this film using material which can absorb some water molecule from the ambient, okay. So it can actually, if this film is put in, or this, if I consider this is a kind of device, if this is put in a humid ambient, of course if it is a moisture absorbing material, this water molecule will get absorbed to this film, okay, and this resonant frequency will shift from the resonant driving frequency fr, okay. So now it is no more resonating at its driving frequency, okay. So this is a typical figure, typical schematic diagram to show the operation of quartz crystal microbalance that we have just seen. This part, this grayish part is quartz, this is the gold, okay, and this grayish part shows the sensitive coating, which sensitive coating means material which can absorb water molecule, okay, and these molecules are nothing but a H2O molecule, okay, and this will cause a change in the mass, or del m, which will cause the change in the frequency, okay, and this frequency will be detected and can be calibrated the accurate percent of RH, okay. So this is a typical operational diagram of a QCM, okay. So initially in the first phase the frequency was del f, I mean the frequency was fixed, okay, when this molecule started getting absorbing on the film, what will happen is you will find that this frequency is shifting, okay, and there will be a kind of quasi-permanent change when these molecules get absorbed, till this frequency will remain this, till this water molecule get dissolved from this surface, okay. So this desorption, so what people does is sometimes they use some external pulses to remove this water molecule from this film because of their hygroscopic properties, okay. So this dependency of this frequency can be expressed in terms of mass as del F by Fr equal to minus del M by M, where M is the mass of the quartz piezoelectric substrate and del M is the change in the mass. Fr we already have seen is the resonant frequency, or we have given a term resonant driving frequency, okay, and del F is the change in the frequency, okay. So by using this equation del F by Fr equal to minus del M by M, we can calculate the change in the frequency with the change in mass on the substrate, okay. Of course, you cannot calculate the mass on the substrate, but what you can calculate is you can find the change in the mass. So initially, say the substrate was weighing m1, okay, and if because of this water molecule, there is a slight change in mass and it goes to say m2, so this del m can be m2 minus m1. But this change can only happen if you have sensitized your film with some moisture absorbing layer, okay. So fullerene, you might be knowing, there is one carbon allotrope, fullerene. They have been effectively used in this QCM kind of devices, but there are other materials also which has been used for these applications. So I have named a few of them. For example, people has reported this polyethylamine graphene oxide composite based QCM devices. Similarly, graphene oxide and naphion composite has also been explored in the QCM based devices. Simple silver nanowire can also act as a sensing material in a QCM based device, okay. Then there are other materials which has been reported for SAW based devices, like a PVA film or composite of another polymer PVP with say cerium oxide nanoparticle or so, okay. Then I mean, this is all about the gravimetry humidity sensors, but there are other kind of devices also, like piezoresistive humidity sensors, okay. So piezoelectricity, I think we have discussed. Piezoresistivity is very similar to that, except there is no change in the electric potential or electric charge, but with the stress there is a change in resistivity of the material, okay. So when you apply a stress, there is a change in the resistance of the material, not the charge. So there is no polarization, there is no charges happening here, only there is a change in the resistance, okay. So this is a typical piezoresistive humidity sensor. These two blocks that you are seeing are nothing but piezo resistors, okay. These are piezo resistors, all right. This is the diaphragm on which a vapor absorbing material has been placed, okay. This has been deposited on this diaphragm, okay. This is known as the membrane type device, okay. So the membrane type device used piezo resistors placed on the top of this diaphragm, okay. As the humidity increases, this was at 0% RH. As the humidity increases, there is a humidity dependent volume change of the polyimide layer, which causes, this is the layer I am talking about, the vapor absorbing material. This causes a deformation of the polyimide bridge substrate bimorph, okay. So there is a deformation because of this weight, okay, because it is gaining more and more moisture, and because of that there is a deformation of this, okay. So because of this there will be a bending of this plate, okay. This is then transformed into an output voltage by the integrated piezoresistive bridges. So since there is a change in resistor, you can transform it into a you can calibrate it as a change in the voltage. Okay, there are various designs available, like simple cantilever kind of design based on this piezoresistive material has been proposed based on zinc oxide nanorods, which is patterned on the silicon. Okay, then for more sensitive devices, piezoresistive Wheatstone bridges has been reported using graphene oxide silicon bilayer kind of devices. Okay, some polymers has also been explored for this application, like P.PSS has been used for piezoresistive cantilever based devices. Okay, then embedded piezoresistive micro cantilever based on polyvinyl acetate has been reported, and polyimide based devices has also been reported again for Wheatstone bridge kind of configuration, where one resistor contains this sensitive film and rest helps in providing the stability to the bridge. Okay, so that is a little bit about piezoresistive humidity sensor. Okay, then there is one more important humidity sensor that is based on magnetoelastic property. Okay, so magnetoelastic properties of a material is nothing but say if elastic material changes its property with magnetic field. Okay, or you can say in vice versa. Okay, so if elastic material changes its property with some external magnetic field, or because of this the stress applied to some material, elastic material, there is a change in magnetic field associated with it, I can say that the material possess some magnetoelastic property. So what people has done is they have cultivated this property of some elastic material to develop humidity sensors. So the transduction mechanism of a magnetoelastic humidity sensor is based on the phenomena that the resonant frequency shifts of the magnetic flux emitted from the sensor in response to a time varying magnetic field is detected. Okay, so the response frequency of the magnetoelastic sensor changes with mass loading within moisture sensing layer while relative humidity changes. Okay, we'll see this phenomena with one example. Okay, so the changes of the mass results in a resonant frequency shift, which can be represented by del F equal to minus F by 2 del M by M, where this is again the mass of the substrate and del M is the change in the mass. Okay, the small change in mass can be detected by monitoring the shift in the resonant frequency of the magnetoelastic sensor. So this is a typical magnetoelastic humidity sensor, where you have a driving coil, a pickup coil and a magnetoelastic ribbon, on top of which a absorption layer is placed. Okay, so if you see what is happening is a AC magnetic field of fixed amplitude is applied to the sensor using a Helmholtz coil. This device is monitored, the signal that I have generated using this Helmholtz coil is monitored using a remotely located pickup coil. So I am talking about this pickup coil. The resonant frequency of the sensor change in the mass of the chemically absorbed layer, and we have seen already the formula for calculating the change in frequency. So del F is equal to minus F by 2 into del M by M. By 2 factor is coming because you are propagating this signal from a drive coil, and then this is again going to pickup coil. So that's why there is a 1 by 2 term. Okay. Then there are various materials that are used for this, which has been reported to possess this magnetoelastic properties, which are Al2O3, say TiO2, and some thin film of some materials, some metals like aluminum and silver. They also possess this magnetoelastic properties. Okay. So with this, I think we have covered several humidity sensors, which includes the optical humidity sensor, where we have discussed various devices based on multiple applications of or multiple ways in which photon can interact with the material. Say a water molecule can absorb the photon energy coming from a diode, or say laser, okay, or LED, whatever you have as a source, okay. Then based on absorption, based on reflection, okay, we also have seen one based on optical fiber, okay. It can also be based on different interferometers. So there have been several reports where this humidity sensors has been designed based on different interferometers, and they are very, very accurate, okay. Then optical sensors can also be designed based on gratings, okay. What we have seen today is basically based on change in mass, particularly like gravimetric sensor, which has two components. One is QCM based devices and another is SAW based devices. In the SAW based device, what we have seen is there are interdigitated electrodes, very similar to the gas sensor IDEs that I have been given example, okay. So this IDE is they act as a one act as a sound propagating element, and another act as a receiver, okay. And in between I have say moisture absorbing film which provide the delay path and all, okay. All these things has been made on a quartz substrate, okay. And this sound propagation is monitored, okay. And if there is any delay, okay, because of this vapor film, it can be calculated, and accordingly the RH percent can also be calculated. Similarly, we have seen QCM based devices where the natural frequency of quartz is used as a sensing parameter, okay. If there is any change in this frequency because of the loading of some humidity molecule or water molecule on the quartz substrate, because there is already a absorbing layer on top, okay, we can calculate the shift in this frequency, okay. Similarly, we have also seen the piezoresistive kind of device, which is basically based on a diaphragm kind of thing, where this piezoresistors are placed on both the side of this this diaphragm. Of course, it can also be made by simply a cantilever, but this diaphragm kind of devices are more sensitive. So you have this film or a diaphragm, which is nothing but thin film of some material or some plate, okay, on top of which you have this moisture absorbing layer, okay. And we have put this piezoresistors very precisely at the corners to pick any change in this any bending of this diaphragm because of the loading of this moisture on this, okay. So by measuring that, I can calculate the what amount of humidity has been absorbed. So accordingly, I can calculate the RH, okay. Similarly, we have also seen the magnetoelastic humidity sensors, where I have utilized the property of a material which is known as a magnetoelastic property, where the magnetic field associated with the elastic film changes when it is strained, okay, or some stress is applied to this film. The magnetic field associated with it changes, or you can understand it as a vice versa phenomena, okay. So we have utilized all this transduction technique to understand a humidity sensor. However, we have missed two important phenomena, which is simply based on change in capacitance. I have mentioned earlier that 75% of humidity sensor in the market is based on capacitive transduction technique, and we have also missed the resistive kind of devices, where the change in resistance of a material signifies the change in the relative humidity, or by measuring the change in resistance, you can find the change in humidity, okay. So we will be discussing all these two devices in the next class, okay. Thank you.